Hello students, welcome to EPG Pathshala. I am Dr. Devrat Mishra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Dielectric Properties 6 from paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. So we will learn the detailed study of complex permittivity. Next, we will learn about the fundamental dielectric relaxation, and you will learn about Debye equation and its complex plane diagram. The dielectric constant and laws are important properties of interest to physics people because these two parameters, among others, decide the suitability of a material for a given application. The relationships between the dielectric constant and the polarizability under DC fields have been discussed in sufficient detail in the previous lectures. In this chapter, we examine the behavior of a polar material in an alternating field, and the discussion begins with the definition of complex permittivity and dielectric laws, which are of particular importance in polar materials. Consider a capacitor that consists of two plane parallel electrodes in a vacuum having an applied alternating voltage represented by the equation V is equal to Vm cos omega t. Here V is the instantaneous voltage, Vm the maximum value of V, and omega is equal to 2 pi f is the angular frequency in radian per second. The current through the capacitor I1 is given by I1 is equal to Vm into cos omega 2 plus pi by 2, where Im is equal to Vm by Z is equal to omega C0 Vm. In this case, C0 is the vacuum capacitance, sometimes also called the geometrical capacitance. In an ideal dielectric, the current leads the voltage by 90 degree and there is no component of the current in the phase with the voltage. If a material of dielectric constant epsilon is now placed between the plates, the capacitance increases to C0 epsilon and the current is given by I2 is equal to Im into cos of omega t plus pi by 2 minus delta, where Im is equal to omega epsilon C0 into Vm. It is noted that the usual symbol for the dielectric constant is epsilon r, but we omit the subscript for the sake of clarity, noting that it is dimensionless. The current phase will not now be in phase with the voltage but by an angle 90 degree minus delta, where delta is called the loss angle. The dielectric constant is a complex quantity represented by epsilon star is equal to epsilon prime minus j epsilon double prime. The current can be resolved into two components. The component in phase with the applied voltage is Ix is equal to V into omega into C0 epsilon double prime, and the component leading the applied voltage by 90 degree is Ix is equal to V into omega into C0 into epsilon. This component is the charging current of the ideal capacitor. The component in phase with the applied voltage gives rise to dielectric loss. Delta is the loss angle and is given by delta is equal to tan inverse of epsilon double prime divided by epsilon prime. Epsilon double prime is usually referred to as the loss factor and tan delta the dissipation factor. To complete the definition, we note that Ix is equal to V into omega into C0 into epsilon is equal to V omega epsilon double prime epsilon 0 A divided by D is equal to omega epsilon double prime epsilon 0 A into E. The current density is given by Ix is equal to Ix by A is equal to omega into epsilon 0 into E. Figure 1 shows the real epsilon prime and the imaginary epsilon double prime parts of the complex dielectric constant epsilon double prime in an alternating electric field. V is shown in the x-axis, I also in the same axis, and IC is in the y-axis. The alternating current conductivity is given by sigma AC is equal to sigma prime plus sigma double prime is equal to omega into epsilon 0 into epsilon double prime plus F into epsilon minus epsilon infinity. The total conductivity is given by sigma T is equal to sigma AC plus sigma DC is equal to omega epsilon double prime plus omega DC. Dielectric relaxation. When a direct voltage applied to a dielectric for a sufficiently long duration is suddenly removed, the decay of polarization to zero value is not instantaneous but takes a finite time. This is the time required for the dipoles to revert to a random distribution in equilibrium with the temperature of the medium from a field-oriented alignment. Similarly, the buildup of polarization following the sudden application of a direct voltage takes a finite time interval before the polarization attains its maximum value. This phenomenon is described by the general term dielectric relaxation. When a DC voltage is applied to a polar dielectric, let us assume that the polarization builds up from 0 to a final value as shown in figure 2 according to an exponential law. Pt is equal to P infinity into 1 minus e to the power minus t by tau, where Pt is the polarization at time and tau is called the relaxation time. I is a function of temperature and it is independent of the time. The rate of build-up of polarization may be obtained by differentiating equation 8 as d over dt of Pt is equal to minus P infinity into of 1 minus r into exponential of minus small t by big T is equal to P infinity into e to the power minus small t by tau divided by tau. Substituting equation 8 in 8a and assuming that the total polarization is due to the dipoles, we get dpt by dt is equal to P infinity minus pt by tau is equal to P mu minus pt by tau. Neglecting atomic polarization, the total polarization Pt, which is a function of small t, can be expressed as the sum of the orientational polarization at that instant P mu t and electronic polarization Pe, which is assumed to attain its final value instantaneously because the time required for it to attain saturation value is in the optical frequency range. Further, we assume that the instantaneous polarization of the material in an alternating voltage is equal to that under DC voltage that has the same magnitude as the peak of the alternating voltage at that instant. We can write total polarization as P tau t is equal to P mu t plus P epsilon. The final value attained by the total polarization is Pt is equal to epsilon 0 into epsilon s minus 1 into E, and we know that following relations will hold good for steady state voltages like P is equal to epsilon 0 into epsilon infinity minus 1 into E, where epsilon s and epsilon infinity are the dielectric constants under direct voltage and at infinity frequency respectively. We further note that Maxwell's relation epsilon infinity is equal to n square. Substituting equation 12 and 11 in 10, we get P mu is equal to epsilon 0 into epsilon s minus 1 into E minus epsilon 0 into epsilon infinity minus 1 into E, or P mu is equal to epsilon 0 into epsilon s minus epsilon infinity into E. Representing the alternating electric field as E is equal to E max exponential of j omega t, and substituting equation 16 in 9, we get dpt by dt is equal to 1 by tau into epsilon 0 into epsilon minus epsilon infinity into E max into e to the power exponential j omega t minus pt. The general solution of the first order differential equation is pt is equal to c into exponential over to the power minus t by tau plus epsilon 0 into epsilon s minus epsilon infinity whole multiplied by E max into exponential of j omega t whole divided by 1 plus j omega t, where c is a constant at time t sufficiently large when compared with tau. The first term on the right side of equation 17 becomes so small that it can be neglected, and we get the solution for pt as p mu t is equal to epsilon 0 into epsilon s minus epsilon infinity into E max into exponential of j omega t whole divided by 1 plus j omega tau. Substituting equation 18 in 10, we get pt is equal to epsilon 0 into epsilon infinity minus 1 into E max into exponential of j omega t plus epsilon 0 into epsilon s minus epsilon infinity E max into exponential of j omega t by 1 plus j omega tau. The simplification yields pt is equal to epsilon infinity minus 1 plus epsilon s minus epsilon infinity divided by 1 plus j omega t into E max into exponential of j omega t. Equation 20 shows that pt is a sinusoidal function with the same frequency as the applied voltage. The instantaneous value of flux density d is given by dt is equal to epsilon 0 into epsilon star into E max into e to the power j omega t. But the flux density is also equal to dt is equal to epsilon 0 into E max e to the power j omega t plus pt. From equation 21 and 22, we get epsilon 0 epsilon star into E max e to the power j omega t is equal to epsilon 0 E max e exponential of j omega t plus pt. Put value of 20 in 23, we get the value of epsilon star is equal to epsilon prime minus f epsilon double prime is equal to 1 plus whole summation of epsilon infinity minus 1 plus epsilon s minus epsilon infinity divided by 1 plus j omega t. Equating the real in imaginary parts, we readily obtain epsilon prime is equal to epsilon infinity plus epsilon s minus epsilon infinity divided by 1 plus omega tau square, and epsilon double prime is equal to epsilon s minus epsilon infinity omega tau by 1 plus omega tau square. It is easy to show that tan delta is equal to epsilon double prime by epsilon prime, which is equal to epsilon s minus epsilon infinity into omega tau divided by epsilon s plus epsilon infinity omega square tau square. Equations 25 and 26 are known as Debye equations, and they describe the behavior of polar dielectrics at various frequencies. The temperature enters the discussion by way of the parameter tau, as will be described in the following section. The plot of epsilon double prime minus omega is known as the relaxation curve, and it is characterized by a peak at epsilon double prime by epsilon double prime max is equal to 0.5. It is easy to show that omega tau is equal to 3.46 for this ratio, and one can use this as a guide to determine whether Debye relaxation is a possible mechanism. Next, Debye equations. Another way to express the Debye equations are epsilon star is equal to epsilon infinity plus epsilon s minus epsilon infinity by 1 plus j omega t. Equations 25 to 27 are shown in figure 2. The conclusion of these equations shows are the following. Number 1. For small value of omega tau, the real part epsilon prime equals to epsilon s because of this squared term in the denominator of the equation 28, and epsilon double prime is also small for the same reason. Of course, at omega tau is equal to 0, we get epsilon double prime is equal to 0 as expected because this is DC voltage. For very large value of omega tau, epsilon prime is equal to epsilon infinity and epsilon double prime is small. For intermediate value of frequencies, epsilon double prime is a maximum at some particular value of omega tau. The maximum value of epsilon double prime is obtained at a frequency given by delta epsilon double prime by delta omega tau is equal to epsilon minus epsilon infinity into omega square tau square minus 1 divided by 1 plus omega square tau square whole square, which is equal to 0, which gives omega p into tau is equal to 1, where omega p is the maximum frequency at epsilon double prime. The values of epsilon prime and epsilon double prime at this value of omega tau are epsilon prime is equal to epsilon s plus epsilon infinity by 2 and epsilon double prime is equal to epsilon s minus epsilon infinity by 2. The dissipation factor 10 delta also increases with frequency, reaches a maximum, and for further increase in frequency it decreases. The frequency at which the loss angle is a maximum can also be found by differentiating 10 delta with respect to omega and equating the differential to 0. This leads to delta of 10 delta del of 10 delta by del of omega t is equal to epsilon minus epsilon infinity into epsilon infinity omega square tau square minus epsilon s divided by epsilon infinity omega square tau square plus epsilon s is equal to 0. These equations show that omega tau is equal to root over of epsilon s by epsilon infinity. By substituting this value of omega tau in equation 27, we obtain 10 delta max is equal to epsilon s minus epsilon infinity divided by square root of epsilon s into epsilon infinity. The corresponding values of epsilon prime and double prime are 2 epsilon prime is equal to 2 epsilon s into epsilon infinity divided by epsilon s plus epsilon infinity, and epsilon double prime is equal to epsilon s minus epsilon infinity by epsilon s plus epsilon infinity into square root of epsilon into epsilon infinity. Figure 2 shows that at the relaxation frequency defined by equation omega p tau is equal to 1, epsilon prime decreases sharply over a relatively small bandwidth. This fact may be used to determine whether relaxation occurs in a material at a specified frequency. If we measure epsilon prime as a function of temperature at constant frequency, it will decrease rapidly with temperature at relaxation frequency. Normally, in the absence of relaxation, S prime should increase with decreasing temperature. Variation of epsilon prime as a function of frequency is referred to as dispersion in the literature on dielectrics. Variation of epsilon double prime as a function of frequency is called absorption, though the two terms are often used interchangeably, possibly because dispersion and absorption are associated phenomena. Complex plane diagram. Cole and Cole showed that in a material exhibiting Debye relaxation, a plot of epsilon against epsilon, each point corresponding to a particular frequency yields a semicircle. This can easily be demonstrated by rearranging equation 25 and 26 to give epsilon double prime square is equal to epsilon prime minus epsilon infinity whole square, which is equal to epsilon s minus epsilon infinity whole square divided by 1 plus omega square into tau square. The right side of equation 35 may be simplified using equation 25, resulting in epsilon double prime square plus epsilon prime minus epsilon infinity whole square is equal to epsilon s minus epsilon infinity into epsilon prime minus epsilon infinity. Further simplification gives epsilon prime square minus epsilon prime into epsilon s plus epsilon infinity plus epsilon s into epsilon infinity plus epsilon double prime square is equal to 0. By using the algebraic identity, epsilon s into epsilon infinity is equal to 1 by 4 into epsilon s plus epsilon infinity whole square minus epsilon s minus epsilon infinity whole square. So the equation 37 can be rewritten as epsilon prime minus epsilon s plus epsilon infinity divided by 2 whole square plus epsilon double prime square, which is equal to epsilon s minus epsilon infinity divided by 2 whole square. This is the equation of a circle with radius epsilon s minus epsilon infinity by 2 having its center at epsilon s plus epsilon infinity by 2 comma 0. It can easily be shown that epsilon infinity comma 0 and epsilon s comma 0 are points on the circle. To put it another way, the circle intersects the horizontal axis E prime at E infinity and Es as shown in figure 3. Such plots of epsilon double prime versus epsilon prime are known as complex plane plots of epsilon star. At omega p tau is equal to 1, the imaginary component epsilon double prime has a maximum value of epsilon double prime is equal to epsilon s minus epsilon infinity divided by 2. The corresponding value of epsilon prime is equal to epsilon s plus epsilon infinity divided by 2. In a given material, the measured values of epsilon double prime are plotted as a function of epsilon at various frequencies, usually from omega is equal to 0 to omega is equal to 10 to the power 10 radian per second. If the points fall on a semicircle, we can conclude that the material exhibits Debye relaxation. A Cole diagram can then be used to obtain the complex dielectric constant and intermediate frequencies, obviating the necessity for making measurements. In practice, very few materials completely agree with Debye equations, the discrepancy being attributed to what is generally referred to as distribution of relaxation time. The figure shows the Cole diagram displaying a semicircle for Debye equation for epsilon star. Epsilon infinity, epsilon prime and epsilon s are in the x-axis, whereas epsilon double prime is in the y-axis, and omega t is equal to 1 is at the center. So students, let us summarize what we have learned in this module. Debye equation was derived and its complex plane diagram was discussed. Complex permittivity was defined and derived. Dielectric relaxation were discussed and described. The behavior of polar dielectrics at various frequencies. Thank you.